Hello, this is our first safety video, and this is, you may have seen it before if you were in one of my other classes, but there's always something more to be gained by seeing a video twice or seeing the information 2, 3, 4 times. We gain a deeper and deeper information level from it. So we have given this training to probably over a couple of thousand electricians over the years. It's NFPA 70E. E stands for electrical. It's 70E is what keeps us electricians safe on the job. Dean Autry and myself went to Alcoa and gave it to their apprenticeship over there. We cover the hazards of electricity, shock, arc, and blast. We also cover the basic protective equipment that keeps us safe. We're going to talk about arc flash, and that in a big electrical event on a circuit that has a lot of energy that can be released. And electricity travels at what? The speed of light. So at 186,000 miles per second, whenever you have high power circuits that short out, you have an arc flash and an arc blast. We're going to talk about those. We're going to talk about a term called bolted fault current. And bolted fault current is the current that instantaneously goes through a fault, like a short line to line or a line going to ground in an instant, in just a few fractions of a second, how much current goes through that circuit. Okay? And then we're going to talk about energized electrical work, exactly what we are expected to work on and what we're not expected to work on hot. And the good news is that's changed a lot in my lifetime. It used to be we worked on everything hot, and we justify it. The good news now is that we're not expected to work on anything hot. Testing is just about it for us. So also I'm going to talk about safety standards and equipment hazards as we move through this. The purpose of this course is designed to improve your electrical safety awareness. So if we're not aware, they call it situational awareness. If we're not aware that something's a hazard, then we can't protect ourselves. If we see a snake laying there, and we don't know anything about snakes, and we don't know anything about poisonous snakes, and it happens to be a copperhead, if we reach down and pick it up, and a good example of that is a kid. A little kid doesn't not know danger. We teach them danger. So if that kid reaches down to pick that snake up, just because that kid doesn't know that that's a hazard, that won't keep that snake from biting them, you know? Same thing for us. We need to understand what a hazard is, what an electrical hazard is, if we expect to protect ourselves. And it gives us enough information to make an informed decision. There's going to be times in your career that you're going to have to make a decision on whether a job is safe or unsafe to perform based on your information. So the more information we have about how circuits work, the bolted fault current, how circuit breakers work, the better off we're going to be in our careers, and we can go home with all our parts. Okay? So normally whenever I give this to electricians, I give them a test, and I talk about circuit breakers. And if you take a circuit breaker, and this happens to be one just like out of your house, and I'll ask them if they've ever reset a breaker, and maybe you have, and that thing trips once a day. Might be whenever 2 o'clock in the afternoon on a summer day, whenever the temperature's 95 plus, that breaker trip. Well, breakers trip on heat, and they don't care where the heat comes from. So environmental heat can cause these to trip, just like the heat from the current passing through them. And then they say, well, yeah, I've reset breakers once a day, you know, and it's just the way it is, maybe for the situation. But then I'd say, have you ever reset a breaker and there'd be a little blue arc come out of there and it'd trip before you get your finger off there? They go, oh, yeah, we've seen that a lot. So I'd ask, you ever think about how much current's going through that breaker at a given time? And most electricians have not. They just know it's different, but they never quantified it. So for a 20 amp breaker, if it takes 10 seconds to trip, and it's based on a GE TED 3-phase breaker. So it looks a little different to this, a little bigger, but it's still a 20 amp breaker. If you reset it and it takes 10 seconds to trip, GE says that it's going to trip between 55 and 100 amps on a 20 amp circuit. Now I'm holding a 15 amp breaker here, but a 20 amp breaker looks the same. If it trips in 1 second, you have 140 to 300 amps going through that breaker. And if it takes a tenth of a second, you have between 250 and 1,000 amps going through a 20 amp breaker. Now, does that change our perspective on the hazard of resetting a breaker trip, resetting a breaker trip, resetting a breaker trip? If we have 1,000 amps going through wire that is only good for 20, and I know we're just starting class, number 12 wire is good for 20 amps according to National Electrical Code. Okay, sometimes 12 is good for a little more than that, but for your home, 12 gauge wire is good for 20 amps. So you're passing upwards of 1,000 amps through that wire. So if you trip it, reset, trip it, reset, trip it, reset, trip it, reset, what are you doing to that wire? What are you doing to all the insulation on the wire in your home? You're heating it up and you're starting to damage it. But if that breaker trips instantaneously, you can have anywhere from 250 to 28,000 amps going through that breaker with number 12 gauge wire. So now you're really heating it up, and these are what you call molded case breakers. Whenever you have an instantaneous fault, ground fault or short line to line, they are designed to explode or disintegrate as a last-ditch attempt to interrupt that circuit where the fault's at from the power source. So that's part of what's designed into them, and they're made to blow up, and I've known them to do that. Okay, in October 1879, I'm going to talk a little bit about history here. Edison demonstrated the feasibility of the electric light bulb, and Edison was pretty ruthless. He was not a very nice person, at least in business he wasn't. I don't know about anything else. But in May 1881, the New York Board of Insurance wrote an article on the danger of fire from electric wires. So this sort of ticked Edison off, and he wrote a response back. He's all mad. And he wrote that electricity was absolutely free from any possible danger from fire, even with the most inflammable material. Now, think about it. How many times did Edison try to invent the light bulb? It was over 300 times. He used over 300 different elements to try to create the electric light. So, what happened to the 299 elements before he finally found the right one? They burned up. They burned up. But he's writing this response because he's all mad about it. So in 1881, one insurer had 23 fires out of 65 textile mills. So if you want to change anything, if you want to change a culture, especially in safety, get insurance involved. So, 1895, back up a little bit. It's only 30 years after his Civil War, there were 5 different electrical codes in New York City. New York City is where the world, where they started wiring the world, in New York City. Right above that, Niagara, is where they put the generators in. Anyhow, with 5 different electrical codes, you know, on one side of the street might be code 2, on the other side of the street might be code 3, the house next to you might be code 5. Didn't take long, a couple of years later, they decided we need one single uniform code for wiring homes. So in 1911, the NFPA became the sponsor. Now, NFPA, National Fire Protection Association, and that's who owns the electrical code today. Now, deaths by electricity. 1890, the first electric chair. It didn't take long to do that, right? So, copper and AC and DC, Westinghouse versus Edison. Okay, Edison was out to disprove Tesla and AC. So he thought, if I get me an elephant and electrocute an elephant, it's going to scare the public. Because the public, for some reason, had a fascination with elephants. The Brooklyn Bridge, when they opened it up, it was the first suspension bridge ever built. The public wouldn't trust it. So there happened to be a Barnum and Bailey circus in town, and the designer of the bridge, the architect, decided that if he marched a bunch of elephants across there, the public would see it was safe and buy into it. Sure enough, that's what they did. They got Barnum and Bailey over there, marched the elephants across Brooklyn Bridge. The public accepted it, and it's still in use today. So with that, the public fascination of elephants, Edison found an elephant. Now, the elephant was an older elephant. They were going to euthanize it anyhow, and with what I understand, they laced the elephant's food with painkillers. But I'll show you that video. You'll have to go to a different section to get to it, but it shows Edison's also known for motion pictures, right? So you got a movie of it. They put copper shoes on the elephant. They hooked it up to a generator. The elephant's sitting there. It's terrible. The elephant's smoking. It falls over, and it didn't kill the elephant. So Tesla and George Westinghouse, they wrote a rebuttal in the paper that the elephant would have died a more humane death had it been killed with a chopping axe. So, excuse me, that backfired on Edison. Now, do we need the National Electrical Code? I know this is the '08 code showing on there. We're using the 2017 code right now in the state of Kentucky and for the foreseeable future. We'll move on up to the 2020 code as soon as the state approves it, but that takes a little while. This here came from a job I was on down in Port Arthur, Texas, which is right next to Beaumont. Beaumont, Texas is known for Spindletop, which is the first gusher oil well ever drilled into. And they have an oil boom town replicated there at Beaumont, Texas. And it's cooler than all get out. If you're ever down there, you got to go see it. And this is how they started wiring homes. So you can imagine back in the early 1900s, whenever they started wiring the world, you've got all these homes already built. All these structures are already there. So they had to run the wire outside the walls. And you see there's two fuses there, those round fuses. So it had 240 feeding the home, essentially 220 volt circuits. Back then it was 110 volts. And where it's drilled through the wall, the wall there, those are tubes, porcelain tubes to keep from setting the wall and the wallpaper on fire. The insulation back then was tar and cotton, tar impregnated cotton that was wrapped around the wires. So if you've ever dealt with any old wiring, it just falls apart. It's been there so long. But you can see, would you want your house wired like this today? I wouldn't. Something here you want to write down. This is really important. It's probably going to show up to a quiz, midterm final near you. The NEC, the National Electrical Code, protects the public and property. That whole book, and I'll get it here. Okay, this whole book, and you can tell I use my book. I've always used it. I made a living with it. This protects the public and property whenever we put our wiring in, when we install it. Now, there's nothing in there that protects you and me as we're doing electrical work. If you notice down at the bottom, it says NFPA 70, okay? Right here, NFPA 70. So that's National Fire Protection Association Code 70. Now, OSHA in 1975 asked the NFPA for help. So if OSHA's asking for help, that's not a good thing, is it? So what was happening? Too many electricians were being killed on the job. In fact, whenever they started wiring New York That's where the first hard hat came into existence. Men took their normal hats and they covered them with a substance called gutta percha. That some of the first golf balls were made out of gutta percha. It'll harden and it has pretty good insulative properties. But if you were a lineman in New York City when they wired New York City, the death rate was 50%. So you could flip a coin on whether you were going to die on the job when they wired New York City in the early 1900s. So nothing was done for the electrical worker for years and years. In 1976, NFPA 70E committee was established. E stands for electrician, okay? Now, I don't know if that's technically correct or not, but that's how I remember it. If it's 70, it's the National Electrical Code for public and property. If it's 70E, it's for us electricians. In 1979, the first edition of 70E was published. It's a national standard now. And for you guys that may be familiar with OSHA standards, it's OSHA 29 CFR stands for Code of Federal Regulations, Subpart S. They defer to 70E whenever they're looking at electrical workplace safety. So, coming to a quiz midterm final near you, NFPA 70E is a standard for electrical safety in the workplace and protects the electrical worker. Okay, so NEC protects the public and property. 70E protects electricians. Now, hazards of electricity, we're going to talk about them. There's three of them: electrical shock, electrical arc, and electrical blast. We're going to talk about these one at a time. And you also have secondary hazards such as fires and falls. I've been in situations where equipment's caught on fire and you are really hustling to get out of that room or away from that equipment. When you're on bigger equipment, if you're on 1,000 or 5,000 horse motor and on a drive, and for whatever reason, maybe the SCR drives catch on fire, you need a way out. And situational awareness for an electrician is so important. You've got to always know what your way out is, and if possible, always have a plan B in case that one route is blocked. Falls, you do a lot of elevated work. I know I spent a lot of time, 29 years at Alaris, spent a lot of time off the floor, 40, 50 feet in the air. Had a lot of cranes that had equipment that blew up whenever I was working on it. It was part of it. Real dirty atmosphere, things go wrong and things happen. If you're not wearing your fall protection, that'd be a long way to fall. So, how often do people get killed by electricity? Okay, right around 1,000 a year get killed in this country by electricity. Okay, how many people get electrocuted? The first way we're going to talk about that people die is what we're most familiar with, is being electrocuted. Okay, so at home, at work, it's 1 every 24 hours. So today, someone woke up, went to work as an electrician, and they'll get killed on the job. At home, it's 1 every 36 hours. And the National Electrical Code gets a bad rap a lot of the time because, I got to get it inspected. I got to have it do this. I got to do that. I got to put those tamper-proof receptacles in. Well, those codes, there's been a lot of lives given for those codes, if you want to put it like that. Those codes come from people getting hurt and killed, either in the home or on the job. So how many of you guys, as a kid, I'll raise my hand, took a bobby pin or a screwdriver and stuck it in a 120-volt receptacle? I still remember we just got a new bathroom in. I was just before I started the school in the first grade, so I'm 5 or 6. They got a gas water heater there right in front of an electrical outlet. And I don't know why. I saw one of my bobby pins there. I saw the receptacle. I don't know why I stuck it in there, but I did. And my little butt was sitting on that metal gas water heater that had a metal pipe ran out to the metal propane tank, okay, which was grounded sitting on the dirt, and it lit my world up. Okay, I was lucky. It didn't kill me. You know how many of you guys have had a similar experience? Kids are kids. So those tamper-proof receptacles that have the shutters that close in on newer homes that people don't like, they did that because of kids getting killed, you know? So how much aggravation is it worth to keep a kid from getting killed? You know, and once you learn how to stick a plug in there, you just line it up, you get it square, you shove it in there, and it's all good, you know? So, GFCIs, ground fault circuit interrupters, we'll be talking about them in the construction class. They came around because of so many people getting killed doing work outside and doing work where they're grounded by code, by the National Electrical Code right here. If you're standing on bare concrete, it's ground. Now, you can't screw a wire to it and make a circuit out of it, but you can dang sure get killed on standing on concrete. So ground fault circuit interrupters, one of the best things they ever came out with, and I've got stories, very unfortunate stories on kids getting killed because of electricians thinking that GFCIs were not important. Okay, so if you take 365 on the job, 243 at home, that's 608 people per year dying through electrocution. The balance of that, 400 give or take, are killed with arc flash arc blast, and we'll talk about that later on down the road. Okay, worker deaths by electrocution, NOS. NIOSH is the National Institute for Occupational Safety and Health, and I spent 10 years in industrial safety at Alaris, and you go to NIOSH to get a lot of statistics to tell you what you need to be working on in safety. So I took a 12-year span here and worked up some demographics. In 12 years, there were 7,300 deaths through electricity on the job from 10 years, 1992 to 02. Over 46,000 were non-fatally injured. Now, these are the people who got electrocuted or got burned, and they went to ER, and it was captured at ER or captured with OSHA. Maybe they had went up front to first aid, but it was at a level that was captured on their accident reports. Now, just imagine how many people got shocked and never sought help, never went up front to get checked out. You know, so many more times than the 46,000 there. 60% were 35 or less. Almost all were men. It's predominantly a male career, you know, although that's changing. 86% were white. NIOSH keeps all those statistics. 40% were on construction, 16% public utilities and transportation. Now, a few years ago, we had that ice storm. So the question comes up, we had public utility people in here from everywhere. You know, bucket trucks from all over the country was coming in. And the question is it more dangerous for a utility to do work during an ice storm that brought all those lines down, they're doing all kinds of work in inclement weather and everything else, or a normal day at the utility? Well, statistically, for most of them, a normal day is more dangerous than a time whenever you've got an ice storm or a hurricane or a tornado that's come through. And what they think it is there is when something unusual happens, it heightens our awareness. A normal day at work, we get complacent. So when I was in safety up at Alaris, my boss and myself, we looked through several years of statistics and we wondered, was a normal day at Alaris more dangerous than, say, a shutdown? And when they have a shutdown up there, they may have 400 people working on a line, cranes everywhere, all taking the equipment down to bare bones and building it back up. Sure enough, the shutdowns that you would expect to be the most dangerous time were the safest time based on their accident reports. The most dangerous time was a normal day. The most dangerous time of day was right before they went home. You know, you got your clubs in the car, you're ready to go, you're almost getting finished with this job. You know how it goes. Second most dangerous time, right before lunch. Most dangerous shift, they work 24/7, 365 up there like a lot of plants do. Most dangerous shift, I've got over 21 years on 21 swing. And I've died 1,000 deaths on midnight. So I knew the most dangerous time was on midnights. Wasn't for us. The most dangerous shift was day shift. So day shift, right before people went home and right before lunch. 12% was in manufacturing. Over a 12-year period, 46% were craftsmen, 15% laborers. Laborers get killed through electrical events on construction jobs, and one of the most common occurrences is a crane moving rebar through a job site. Now I'm talking about a sizable job site. So you've got a 20-foot long bundle of rebar, you've got a mobile crane working it through the job site, and where's the laborer? The laborer's on the front end of that 20-foot bundle guiding it so it won't hit anything. But guess where the boom is? The boom's sticking up. And on a sizable job site, they've got temporary high lines ran throughout the job site, and it's normally something like 13,800 volts to supply temporary power to build the powerhouse or build the plant, whatever they're working on. So sure enough, that boom runs into the line, energizes the crane. The crane's on those huge rubber tires. It's pretty well insulated. But guess what's not insulated so well? That laborer that's holding the end of that bundle of rebar and walking on the ground. So it's called secondary contact. Primary contact will be the boom into the high lines. Secondary contact is the laborer touching the rebar and getting electrocuted. 53% with supervision was present. How many of you guys have been working with a supervisor and the supervisor's in your ear going, how long will it take? We need to hurry up. We've got to get this out. Excuse me. Can that cause us to make a bad decision? Yes, it can. Yes, it can. So we have, in electrical, we have to be on guard for that. 47%, nobody was looking. I've heard it said, and you probably have too, the definition of integrity is what we do when nobody's looking. Several years ago at a facility, it was not one of your better facilities at the time, but a supervisor came up missing. So they got to hunting for him, and he had been electrocuted behind some equipment. He was trying to change out a cartridge fuse barehanded. Let me grab a cartridge fuse. This is a cartridge fuse, a 600 volt cartridge fuse, 480 volts normally. So, come to find out they'd had trouble with the equipment. They had tried to fix it for whatever reason. They couldn't find a problem or didn't find a problem. So all they had to do is just put a new fuse in or two fuses and get it going. So someone showed that supervisor, because I promise you the average person would not do this on their own. Someone showed that supervisor, hey, if you don't touch any metal, and if you just grab it in the middle because this is insulated and pull it out and shove a new one in, you can get going and you don't have to call me in, you know? Because I've been called in so much, I don't want to come in no more. I don't know that's what happened, but I'll bet I'm not too far off. So the first time the supervisor changed it out, you know, he was really careful, right? But what did supervisors start doing? You know, when we're around a hazard, the more we're around it, the more we think that we're not going to get hurt. So we had a couple or three things come to play here. Then pretty soon the supervisor was yanking it out, putting a new one in. He was a hero. But all he had to do was be touching that fuse cap one time, and it cost him his life. Now, 99% involved AC. Alternating current is the dominant power distribution that we use in this country. Only 1% were electrocuted by DC. I've heard it said, well, AC sucks you to it and DC blows you away, or AC blows you away and DC sucks you to it. They're both bad. I don't know that either case is true. I do know when you get the voltage high enough, it blows stuff apart. It blows fingers off, it blows arms off, it blows legs off. High voltage, it doesn't matter. Either one is terrible to come in contact with. 2/3 of it was on less than 600 volts or greater than 600 volts. 1/3 was less than 600 volts. In the below the 600 volt segment, okay, and that's basically what we talk about mostly in this class, a little over half occurred in manufacturing, a little over half involved 120 to 240. The 120 to 240 is important because when you see that many people getting killed on 120, it's awfully easy to get lulled into the mindset of, hey, I work on 7,200, I work on 13,800, I work on 480. It's only a 120 volt receptacle. I can change that out barehanded. Well, maybe you can, but for how long? How long can you change it out hot and not make a mistake, not being against, leaning against a piece of metal, not having a hole in your boot, not be standing in a little bit of water? 54% of these fatalities and injuries came from working on 120 to 240. Now, bad habits. We got a lot of stuff going on here, and I'm going to give you a couple of seconds and let you look at this picture. First off, where's he at? It's a swim up bar. Okay, if you haven't been to one, you got to go. Okay, pretty cool. Get you another margarita, get you another beer. You don't even have to get out of the water. Now, how deep's the water? Excuse me. If you look, you can see the high water mark on his clothes. He's wet up just under his armpit. He's barefooted, And I talk about a plan B and safety. Also, give him credit where credit's due. He's got his safety goggles on, But he's on an aluminum ladder, right? Now, if you're in a pool of water, first off, totally pure distilled water is an insulator, right? Should have learned that in circuits 1, circuits 2. But what's in pool water? It's one of two things. It's either going to be chlorine or salt. Either one is an impurity, and both of them conduct. So he's got a great conductor with an aluminum ladder. He's connected to it because he's wet and barefooted, and he is in a pool water, so he is absolutely 100% grounded using a 120 volt drill. Now, with a 120 volt drill, he's got plan B. Now, maybe you see it, maybe you don't. But that bartender back there looks to me like he's holding the cord. Excuse me. So you know what the conversation was before he went up there. Now you watch me, and if anything happens, you unplug it, right? You unplug it. Well, I don't know about your bartender, but the last one I had didn't work at the speed of light, and speed of light's how fast electricity goes. So what kind of a plan B is that? Not a very good one, okay? Two kinds of electric shock, discomfort and death. Excuse me. I will give you a second to write this down because this is coming to a quiz, midterm, final near you. There's only two kinds of electric shock, discomfort and death. I didn't know. Oop. That drill, the video there will be on a separate video, and this example and the next example will be on a separate video, okay? Now, we're going to talk about insulators. And if you ever watch a guy going down the street, one of Kenergy or OMU Highline workers, and they're up there with gloves on and they're doing work on energized lines, okay? So the question is, and I'll work us through it whenever I do the other video, and it'll be a separate video on your blackboard. Does any current flow whenever they're using those gloves? Because they have their gloves tested, they have their bucket truck tested, they call it high potting it. They test it for sometimes 100,000 volts or more, depending on what it's supposed to be rated for. But this testing laboratory says there will always be some current flowing, even when the best available insulator connects points of different electrical potential. So what's that telling us? That's telling us there's no perfect insulator. So this is also important. Coming to a quiz, midterm, final near you. There is no perfect insulator. Those porcelain insulators on all the highline poles, they do pass some current, okay? To ensure complete safety to linemen, the resistance of the equipment needs to be large enough so that only a few hundred microamps will flow through a human body when either a worker in the bucket or the bucket itself comes into contact with a high voltage line. Wow. Now, so if those gloves, those big old gloves, okay, I've got one right here, okay? That big old glove with the leather on it, if that's passing electricity, why doesn't the guy feel it, And also, if it's passing electricity, do we have a working circuit? We do, okay? So we're going to talk about why the worker doesn't feel it. Now, this guy here, the drill might be insulated, but as you'll see when you watch the other videos, this guy has some current passing through him. He just can't feel it. So let's back up a little bit and talk about Ohm's law and skin. It's always changing. Ohm's law, current equals voltage divided by resistance every stinking time, okay? Ohm's law, Ohm's law, Ohm's law. Top troubleshooters really understand Ohm's law. It's a sixth sense to them. Your circuit voltage is normally constant, so you're working on 120 volts, 240, 208, 480, 575, 13,800. All those voltages are constant, okay? But what's not constant is your resistance, What kind of shoes do you have on? Do they have holes in them? Have you had them for 2 or 3 years? Are they about worn out, or are they brand new? Are you standing in some water? Do you have a metal shard? Have you walked through the machine shop and picked up a screw in the bottom of your shoe sole? If you have, and most of us, our feet sweat. So if our feet's sweating and we have a piece of metal in our shoe sole and we're standing on concrete, which is what? It's ground by the NEC, then do we stand a higher chance of being electrocuted that day? Yes, we do. Are we soaking wet with sweat? Now, when you're in circuits 1, I know what they teach you. They teach you current takes the path of least resistance, okay? Excuse me. From now on, that is not true. It's been true up to now, current takes the path of least resistance, but from now on, current takes every path, okay? I can prove that, okay? So if I make a comment like that, I should be able to prove it. Fair enough? Okay, you and your neighbor, all right? Or let's just do your house. Your house, okay? We don't have many sports going on now, but you got something on. Last week it was golf. It's PGA, okay? So you're watching the PGA on your brand new OLED 60-inch TV. Takes about 600 watts to run, okay? Power, 600 watts. Power is power. Your daughter or significant other or wife upstairs in the bedroom is getting ready to dry their hair with that 3 megawatt hair dryer. Now, if current truly takes the path of least resistance and you've got a 3 megawatt hair dryer and you got a 600 watt TV, which voltage is constant, which one's going to pull more current? Okay, which one's going to have the least resistance? Whichever the one that consumes the most power will be the lowest resistance. Okay, so that 3 megawatt hair dryer, as soon as she turns that on, if current truly took the path of least resistance, what would happen to the PGA? It would go off. Your TV would go off because now she's sucking it all up with that 3 megawatt hair dryer. But we know that doesn't happen, right? No, it doesn't happen because she's going to dry her hair and you're going to watch the PGA and everything's going to be great. Now, current takes all paths, you know, and if you've got kids, I know they take turns going out running recon, making sure that all the lights are on in the house and they're all working, right? Yeah, I go through that too. Anyhow, if one's turned off, they want to make sure it works and they'll turn it on. If current took the path of least resistance, we couldn't do but one thing in the house at a time, right? But we do everything. The refrigerator runs, furnace runs, cook stove, microwave. Now, it truly took the path of least resistance. Let's do it house by house. If you're out there, if you're just watching TV and your neighbor has a buzzbox welder in the garage and he wants to weld up his trailer, his hunting trailer, as soon as he strikes an arc, your house is going to get shut off. But that doesn't happen, does it? Because he can weld and you can watch TV at the same time. Current takes all paths, okay? So from now on the rest of your life, current takes all paths. It does not take the path of least resistance. It does, but it takes all of the paths at the same time. Okay, so what's that mean? That means that if we are out there working and we are leaned up against a piece of metal, okay, our skin contact on that metal just reduced our resistance to ground, okay? If we're soaking wet with sweat and we lean up against a piece of metal, okay, we have a lower resistance. Most of our resistance resides in our skin. We'll talk about that here in a minute, but if we get a cut on our hand, there goes half our resistance. So, coming to a quiz, midterm, final near you, you are never more than a constantly variable resistor to any circuit. A constantly variable resistor to any circuit. Okay, clamp-on current. That's one of the worst currents, worst conditions that an electrician can ever be in. Our muscles work from electrical stimuli from our brain. The reason I can work my finger back and forth, open and close my hand, work my elbow is because my brain sends an electrical impulse to my muscles and it makes them contract or it releases. Contract, release. The brain's doing that. Clamp-on current happens between 10 and 30 milliamps. And when we get an outside source of current through our muscles, it's going to contract. That's why a lot of people say, it's not why, but a lot of people say, well, AC sucks you to it or DC sucks you to it. No. Most of the time, when we're doing something, when we're working, we're reaching for something. We're reaching for a wire. We're reaching for a fuse. If we touch it like this and we get the clamp-on current going through our muscles, they're going to contract, okay? Most time we're reaching, then when we contract, we can't let go. Because you see, the current out of this circuit is overriding what our brains tell it to do. Skin, heart, muscles. Okay, skin's the largest organ in your body. It weighs about 7.5 pounds. Its main job is to keep bacteria out. And if you ever have to go to a burn unit, I had to go to a burn unit twice for employees during my 10 years in safety up at Alaris. If I never go back to another burn unit, it's okay with me. But one of the first things that a doctor will talk about is infection setting in after a burn. So if we're in an electrical event and we get a place burned the size of a 50-cent piece or a half a dollar or bigger, we're going to have a skin graft more than likely. So the chances of infection setting in is pretty high. MRSA is something that's out there now. I mean, it changes people's lives. My mama contracted it in a hospital operating room. She had 23 operations over a period of about 20 years. Everything from her pelvis to below her knee was artificial. It changed her life. And doctors are very concerned in the case of an electrical event of MRSA setting in. The worst kind you get comes out of a hospital operating room. And when my mom first contracted it, there were 5 different antibiotics that would keep it beat back. There's no cure for it for that type. By the time she passed away at 97, she had a good long life. At 97, the MRSA had mutated to the point there was only one antibiotic that would work. So we owe it to ourselves not to be caught up in an electrical event. It can change our lives. Skin, keratin, that's the yellow part on our skins. Normally it's what calluses are made of, and that's where the bulk of our resistance resides in, is the keratin in our skin. There's no insulation or voltage rating on it. Surface area, like we talked about, the more surface we've got contacted with ground, okay, if this is the side of a cabinet and I'm leaning against the cabinet, that is a bad practice. And we want to stay isolated from ground as much as possible when we're out there doing electrical work. So it all comes down to Ohm's law and surface area. If I'm touching it with the end of my finger, excuse me, that's a pretty high resistance connection compared to my whole hand or my sweaty shoulder. So always think about the surface area you're contracting. Punch through is what happens to skin when you get up around 2300 volts. When you get over 600 volts, the normal distribution is 2300, 4160, 4160 volts, 6600 volts, 13,800 volts, and then on up from there. But when you get to 2300, you're going to blow through it's going to blow through your skin, and then you have very little resistance inside your body to stop any current. Now, heart surgeon came up with this, and I would think a heart surgeon would have some pretty good credibility. And he maintained that dry skin had a resistance of about 100,000 ohms. But if it were moist, that that drops down to 1,000 ohms. And then if any of you guys have had sleep studies, I've had to have a couple, they scratch around on your head and they put the electrode paste on there for the electrodes. That drops it down to half. But look here, on an implanted cardiac electrode, only 10 ohms of resistance. So once you get through your skin, all you have blood and muscles. And blood has a saline content or salt content. So if we compromise our skin, if we have a cut, how many of you guys have looked around and you saw some blood while you're working, you look and you cut your hand? Well, do you stop working or do you go ahead and get the job done and then dress your wound up? Well, unless it's really bad, you need stitches or something, most of us keep on working. But if you have a bloody hand or you have compromised your skin, the normal human has 1,000 to 1,500 ohms. This is coming to a quiz midterm final near you. 1,000 to 1,500 ohms hand to hand. If you cut your hand and you come into contact with metal, where's half that 1,000 to 1,500 gone? Now you're down to 500 to 750 ohms. That shock you took yesterday without a cut might have just hurt like hell. But today, that same shock on that 120 volt receptacle could be fatal because you had skin that was compromised. This will show up on a different video. This shows a person coming into contact with high voltage lines, and I will walk you through that on a different video. The heart, if we're lucky, it'll beat 2.5 billion heartbeats in a lifetime. And you have two sections at the top. You have the atrium and the ventricle, or you have two atrium at the top, two ventricles at the bottom, okay? So as little as a let me back up, okay? Here's how they work. Whenever they're relaxed, your whole heart's a muscle. Remember me telling you that an electrical stimuli from your brain will make your muscles contract? Well, your brain sends an electrical stimuli down to your atrium, the top. It's the SA node at the top of your atrium. And that makes the top of your heart contract. And when it contracts, it's full of blood, it squeezes the left atrium, squeezes blood into the left ventricle, and the right atrium squeezes blood into the right ventricle. And once it gets all the way contracted, it waits for just a fraction of a second, and then your brain sends another impulse down to the VA node, and it showers an electrical impulse around your ventricles, okay? And then the ventricles contract, and they squeeze blood out. One goes to your lungs, the other one goes to your circulatory system, and then everything relaxes, and then the whole thing starts again. Your brain sends an impulse to the SA node showers electrical impulse down on the atrium muscles, they contract, squeezing blood down to the ventricles. Then a fraction of a second later, your brain tells the VA node, hey, we need to contract them, contracts them, squeeze your blood out. As little as a 60 milliamp outside current can interrupt that electrical system. Okay, so that's why a shock through your chest is so dangerous. Fibrillation, ventricular fibrillation, is a condition where your heart jumps out of time. Fibrillation comes from a Greek word which means worms. And according to doctors and people that tell me, a heart that's fibrillating looks like it's full of worms because there's no consistent beat. It's just sitting there jumping around, twitching. So that night light that y'all had when y'all were kids is a 7.5 watt night light, and it pulled 62.5 milliamps of electricity current. Pacemakers are 10 to 40 microwatts. That 7.5 watt night light you had, if you get that current, 62.5 milliamps through your chest, you could be in a world of hurt. That's where the hand-to-hand contact with an electrical circuit is so dangerous. A pacemaker is 187 to 3/4 million times, or excuse me, that 7.5 watt night light is 187 to 750,000 times more than a pacemaker. My next door neighbor got a pacemaker a couple of years ago, changed his life. He feels great now. But what's a pacemaker do? It changes the rhythm of your heart. It shocks your heart. So if we're passing a current like that through our chest, then we could easily die from that. That could be a fatal event. Test as little as 1.2 volts with full immersion can be fatal. I'll have another video on that. So you're going to have 4 or 5 more videos that complement this PowerPoint. Okay, muscles, uncontrolled contraction, okay? 3 to 10 milliamps will cause us to jump, okay? Is our skin compromised like we talked about? In 1950s, we did not know, they did not know, with electrical shock, what would cause injury or death? How much current would stop a heart? How much current would stop breathing? No one knew. So Charles Dalzell, if you want something interesting to read, you can Google him, and it's very interesting. He was out at University of California, Berkeley, and he ran human experiments. And these experiments are illegal to run now, thank God. But he got student volunteers in 1961, and how it worked was they energized a plate. It was hooked to one side of a power supply, and they had the other hand hooked up to the other side of the circuit. And the students agreed to be shocked. So he would start out with buttons, and he'd start with a very low current, and then he'd up it a little bit, and a little bit, and a little bit. Excuse me. And then all of a sudden it hurt, and the student would pull their hand off. And the students agreed to this, so there had to be dope involved, right? So once they couldn't keep their hand on it anymore, they had another student come in and hold the first student's hand on it to get into the threshold of pain. And what they came up with was, and it's terrible, it's against the law now, but we got the information, I guess. Less than 1 milliamp to the average person is imperceptible. So think back on those gloves, that highline worker, okay? If that highline worker's up there with those gloves, it has less than 1 milliamp because there's no perfect insulator, right? Excuse me, rubber gloves. You think they're perfect? They're not. They're passing current, but if it's less than 1 milliamp, if it's just, let's say it's 40 microamps, you're not going to feel it, okay? So is that good information? Heck yeah. 1 to 3 milliamps is the perception threshold. I don't know if you've ever touched a cabinet or not, an electrical cabinet or a home appliance, and you barely feel a tingle, something's wrong. Well, probably that motor's grounding, you know. If you've got a garbage disposal on a stainless steel sink that's going to ground, but it's not grounded enough yet to trip the breaker, it'll give you a tingle. Or a refrigerator. 3 to 10 milliamps is going to start muscle contraction, okay? But the real fear, excuse me, the real fear is the 10 to 30 milliamps, which just clamp on it. You're not going to let go. Now, this here shows the threshold of perception. Every dot is a different person. The two lines there, one's for men, one's for women, okay? But every dot is a different person on when they felt that current. So what's that mean? We're all different, sort of like that sleep number bed. What's your number? Well, I don't know. What I feel now may be a lot less than what you would feel. Maybe you have more calluses. I talk for a living now, so I don't have the calluses I used to. So you might be able to go on up the scale there before you feel it, but I might feel it pretty quick. Now, women, they take better care of their hands, thank God. You know, who wants alligator hands on a woman? Anyhow, they put lotion on their hands. They have a lower resistance because they take care of their skin. It's moisturized. They will feel it quicker than we do. So the point of all this is, if someone's telling you they're getting shocked and you walk up and touch it and you don't, which you shouldn't be doing that, right? What should you do? You shouldn't walk up and touch something if someone's saying they're getting shocked. Pull your meter out. Use your meter. Take it to the bank. If they're getting shocked, you need to put your meter on it, find out what's going on. Now, let go current means maybe they'll pull off, maybe they won't. Same thing here. You've got all these dots stretched out all over the line there, and we're all different. So what you might be able to pull off of, someone else can't. Very unfortunate. I was talking about this. I was giving this training up in Ohio to an aluminum plant up there, and it was time for break. So they were all maintenance, mechanics and electricians. So it's time for break. All of them left the room but one. One of them walked up and said, Marty, I know what you're talking about with let go current. He had these 3 fingers gone. I said, my Lord, what happened? He said, we were pulling wire in a hot 480 volt panel, and we were soaking wet with sweat, had those white Tyvek suits on. He said, I slipped and my elbow rammed against the side of the panel and my hand hit the buswork. Now the buswork's where your breakers hook, connect. He said, I was trying to scream, I couldn't scream. I was trying to pull off, I couldn't pull off. He was into clamp-on current. He said, I saw my fingers burn off one at a time and hit the floor, and when the third one burned off, I could pull free. Now, and a couple years later, I was back up at the plant and I was checking on them, and they said, man, you didn't hear? I said, hear what? I said, he passed away. He was just in his 40s. So you have to wonder, I don't know, I'm not a doctor, but I know if I were watching my fingers burn off one at a time till the third one hit the floor before I could pull off, my heart would be stressed. So did that event cost him years of his life? I don't know. But the main thing is there's safe ways to do this work if we'll just get the training, get the equipment, and do it in a safe manner. There's very few jobs that's too dangerous to do, given the right training, the right equipment, and the right people. Current magnitudes, 10 to 30 milliamps, you're getting paralysis of the arms. So your arms are going to be sucked up, you're into clamp-on current, it's totally out of your control at that point. 30 milliamps, your chest is going to start pulling in because you have chest muscles. It's going to start suffocating you. Okay, this here is a picture of old Sparky. Eddyville, I was lucky enough to go on a tour down there one time. I saw the one they use. A carpenter here in Owensboro actually built that. I, for one, maybe it's my electrical background, I'm not a believer in electrocution for capital punishment. It's a terrible way to go. But the armrest there, that chair is made out of oak. And I looked underneath the front of the armrest, and you could see where people dug their fingers into the oak when they were electrocuted. Now, I think that's a horrible way to go. I mean, people bleed out of every orifice they've got. I mean, it's horrible, horrible. There are more humane ways. Just my commentary there, okay? Throw rocks at me if you will. But that current going through them is about 2,300 volts, and it's around 4 to 5 amps of current that's passed through the human body. But it's enough to make the human fingers dig into the oak, solid oak armrest. Just this here came off of a job I was on. It's a pretty cool job. I was on a ship. It's called the Wilmington. It's an Exxon ship. It's a sister ship to the Exxon Valdez. Some of you guys might know of the Exxon Valdez. It was one of the worst environmental oil spills in history up in Alaska. And this ship here, again, was a sister ship, but we were on there doing arc flash analysis for Exxon because they had their third engineer was killed on a test bench while working on this breaker. Now, you might think, well, you know, he got killed on that panel. No, he had to change the breaker out. The breaker's a sizable breaker, okay? I'll show it to you when you come in for lab. But it had what they call a shunt trip on it. You might think, well, he was killed on 480. No, he was killed with a little bitty, what we call a cheater cord, where you hook it up to a 120 volt little bitty coil to test a trip. And the hot wire came loose, and he reached out there and grabbed it. And, you know, you're on a ship, you're on a metal deck. He got electrocuted right there in the electric shop trying to test the 120 volt function of that breaker. The sad part was he didn't need a shunt trip. You just tape them off if you don't need it. He didn't know that. He was trying to test it to make sure. It totally changed the safety culture of that ship and Exxon. They started giving them mouth to mouth by federal law. Once you start giving mouth to mouth, you have to keep it up until life support arrives. It took 45 minutes for life flight to get out to the ship. Totally changed the culture of that ship. Okay, 60 to 70 milliamps is fibrillation threshold. If you get 60 to 75 milliamps through the chest, 0.5% of the population coming to a quiz, midterm, final near you. 0.5% of the population will go into fibrillation. And there's never been one case of fibrillation outside of a hospital operating room or in recent times with an AED, automatic electronic defibrillator. And they're great. We've got one here. We've got one here in this building for the lab. And I'll show you whenever we come together for lab. Outside of those two, hospital operating room where they can stop your heart and start it, or an AED, there's never been one case of survivability once you go into ventricular fibrillation. At 250 milliamps, 100% of the population is going to go into fibrillation. So, 15 amp breaker, 250 milliamps, 1/4 of an amp, okay? 4 times 15 is 60. 60 people could go into ventricular fibrillation on this 15 amp breaker and die, and you wouldn't trip it, okay? It does not take that much to kill us. That's the point of all this. So, at 4 amps, your heart's going to be paralyzed, and at 5 amps, you're going to start experiencing tissue burning, and the 2300 volts will be punched through. Okay, we're never any more than a constantly variable resistor to any circuit. EH work boots are not voltage rated. They're called electrical hazard work boots. You can look into tongue. Whenever you buy boots, it should have the EH label in there. And they're tested at 14,400 volts RMS, root mean square, 60 hertz. For 1 minute, and they expect less than 3 milliamps to flow through the boot. What they've got, these are not EH rated. At least last time I looked, they weren't. No. But EH rating has a hard plastic shield above the sole. So if you're out there walking around in a maintenance shop and you get a nail or a screw in here, like I was talking about before, and it's close to coming through, but it's not quite through, and your foot's sweating, are you at a higher probability of being electrocuted if you come into accidental contact with an electrical circuit? Yes, you are. The EH rating has that hard plastic barrier that if you get metal shards or a screw or a nail going through your sole, you have some protection there. No voltage rating, it's secondary protection, not primary protection. Okay, they're only tested in the lab on the models. Each individual boot is not tested, there's no voltage rating, and from the time you put them on, they start aging. So, current magnitude, less than 1 milliamps imperceptible. 1 to 3 milliamp is where you're going to start feeling it. 3 to 10 is going to contract your muscles, but you'll probably still be able to come off. Most severe condition, 10 to 30 milliamps. We're going to be in the clamp-on current, coming to a quiz, midterm, final near you. 10 to 30 milliamps, paralysis of your arms or clamp-on current. 30 milliamps, you go into respiratory paralysis. In other words, your chest muscles are going to start contracting. 60 to 75 milliamps, 0.5% of the population is going to go in fibrillation. 250 milliamps or 1/4 of an amp, every one of us will go into fibrillation. 4 amps, heart paralysis. 5 amps, tissue burning, punch through. Okay, what does this mean to you? Rock it in. You have, when you get around these factories, that are sizable, they have circuit breakers that look like washing machines. They're literally that big. And they have a rocking system with a screw and a pinion that either push them back horizontally or push them up vertically. And the way they make connection, they have like a trailer ball and then fingers that actually connect the circuit. Depending on where you're at, rocket in means different things. If you're around here, a lot of the time, rocket in means you're closing the breaker and energizing the circuit. To give you an idea, if you're at Alaris, they have 1,200 and 2,000 amp breakers at 13,800 volts. These are sizable pieces of equipment. So if you're energizing a 13,800 volt circuit, then you need to understand that's what you're doing, because a lot of the time we're on radios. So if you don't understand what something means, you need to ask and make sure before you take action. In other parts of the country, rocket in does not mean turn it on. Rocket in, you have a rocking motor, it looks like a 1/2-inch drill motor. You're going to make those trailer balls and fingers connect. That's all you're doing. You're not energizing the circuit. One way you are, another way you're not. So if you don't know what rocket in means or anything else, the right thing to do is ask for clarification. Do you want to close a breaker? What are you talking about? That's the time you prevent an injury before. I know a part of my job was running a mobile crane a lot of the time when we were setting motors. I loved that job. It was something different. But one time I had a guy on the left of the load doing this, one on the right load doing this, and the one in the middle doing this. So instead of picking one, the right thing to do is throw your hands up, go, 3, I want one, Let one person give you direction. If you don't know, get clarification.